set.
Hello everyone, good morning. Will and Joe. I'm the Chief Engineer for Spacecraft Thermal Management.
My name is Scott Klinker. I'm part of the Proof of Concept team.
My name is Carlos Macias. I'm part of the spectrometer team.
My name is Eugene Shumakov. I'm from the nickel oxide team.
And today we're going to talk about our project. So this is what we're going through today. To begin, we're going to start with an analogy. So has anyone seen or anyone been in a 787? Right? Yeah, that's good. So you must have played with the windows, right? That's like their main feature. So for our project, we're trying to do that, but for a spacecraft. And it turns out this device, called a variable electrochromic device, has very big potential in attracting and repelling heat fluxes. It uses an electric current to change its emissivity levels, so you can alter how much light goes in, or how much heat goes into a system, and how much heat is rejected from the system. And how this works is, for our project, we have two main chemical slides, or chemical layers. One is nickel and one is tungsten. One acts as the cathode, one acts as the anode. What's interesting about the cathode is if the electrons are removed from it, it'll change into a dark blue color. While if the anode adds in electrons, it will change into a dark brown color. So if we have a medium of electrolyte that'll transport these electrons in the form of lithium perchlorate, this combined effect will help. It's more or less like Polaroid glasses. If you have one on top of the other, it'll block more light. And that's what we're trying to do here. We're trying to increase how much heat flux we can block out for a space satellite. But to do that, we need to start with improving our manufacturing processes, our experimental hardware designs for quality control, and improving our how well our slides will change color. So that's what our team is doing this year. We're trying to just improve on that, and we're building up to this point where we can actually build an actual mock-up or a prototype of this thin film or variable electrochromic device. Our system breakdown is we have two teams. One is the chemical team, which consists of mostly chemical engineers and MSCs. They're in charge of developing and manufacturing the chemical slides. And the mechanical team is in charge of testing out these slides in the form of the spectrometer team, proof of concept team, and our voltage testing team, which is our salt quality control team. With that said, I would like to pass it off to Eugene to talk about our chemicals.
So the main goal of our team was to achieve a fine deposition of nickel oxide and tungsten onto FTO and ITO slides. And the three main steps was to first clean the slides with the RCA clean, which involved the hydrogen peroxide, submerging the slides in hydrogen peroxide, getting rid of all the impurities on the surface. Followed by chemical bath deposition, where we submerged the slides on wires into the solution in the beaker and waited for our chemicals to react and for the desired either nickel oxide or tungsten to precipitate onto our slides. After this, we would take out the slides, rinse them with deionized water, and anneal them to get rid of all the moisture from within the material. And so as you can see here, here's some on the right. Here's some of the slides. That's before annealing. So originally they were clear, and here we can see they turned. We have some deposition on them. On top is the nickel oxide and tungsten slides on the bottom. So here is on the top is before annealing. So as you can see, there's a color change as the moisture is driven off. On the left is nickel oxide on the right, also nickel oxide, and tungsten in the middle. And here's some more pictures. So during the composition of our mixtures, we achieved varying degrees of deposition. So you can see that some of them are darker than others. We got nickel on the left and tungsten on the right. And with that, I'll pass it off to Scott.
Alright, thank you. So I'm part of the proof of concept team, which means creating a prototype to test the feasibility of our concept so it can eventually be put on like CubeSats or nanosats. So we start off with our SolidWorks model, which consists of a clamp with 2 slides and a spacer in the middle. We started with 2 different designs after our SolidWorks model. We have one that uses a 1-clamp design and another one that uses a 2-clamp design. We're leaning more toward using the 2-clamp design as it's able to hold the slides more firmly together than using only a 1-clamp slide. In addition, we have different spacers. In this one, we're using an O-ring spacer. We're also considering using a square spacer, as that would be able to maximize the amount of color change that would be available for us to use on the slide. And with that, I'd like to pass it on to Carlos.
Thank you, Scott. So I'm part of the spectrometry team, and ultimately we're developing a testing rig so that we can define if the chemical processes that our slides undergo are effective or not. And we're going to do this by noting absorbance levels. So this past quarter, we've developed a testing method with our advisors that helps us get data that helps us make sense of the different slides in order so that we have a way of quantitatively measuring how effective they are. We also just recently finalized the designs for the parts that we need to print, because it's a combination of parts that we print and parts that we are going to purchase. For example, we have here, which is our microcontroller base design, and this is our lens holder design. Moving forward, we will start manufacturing by printing and putting it all together in the next couple of weeks. With that, I'll pass it on to Will.
Yeah. So I'm part of the voltage testing team as well. So what we do is we isolate. So the finalized design will have 2 slides, one nickel and one tungsten. So what we do is we isolate one slide with a platinum electrode and test the chemical properties off of that. So what we look for is color change, the power usage, the rate of color change per cycle, and its overall entire life cycle. So what we do is we test these slides at 1.25 through 1.75 volts for 20 cycles. We'll flip the voltages back and forth, changing the currents. So I'll alternate from changing to dark, changing to bright, to a brighter color. We use a platinum as the electrode because the chemical properties of platinum work better than most other metals in terms of transporting electrons. And currently we're developing a potentiostat to help further refine the testing processes, since our voltage system needs a little bit more refinement. So we have a little GIF here. It's sped up like 0.2 times faster. So if we flip the voltage one way, that's the color changes to. If we flip it the other way, it turns to a bright, nice, clear color. So that's what our tungsten slides look like on the right over here. And this is what our nickel slides look like. If it were a little darker, you would see this is blue and this is a little bit brownish. That said, I'd like to pass it off to Scott to talk about it, or Carlos to talk about it.
Our timeline is broken into 2 sections. We have the mechanical team, we have the chemical team. So mostly the chemical team is focusing on refining their chemical processes. So they've been on track most of the time. The mechanical team, we've had some setbacks, as you can see, they're marked in yellow, but currently we're all on track. The X's indicate our deadlines. We have 2 coming up for the mechanical part of the team, but mostly very proud of our team because we are on track. With that, passing on to Scott, talk about our budget.
Thank you. So we have budgets for the chemical team and the mechanical team. Our chemical team budget's around $2,000, as we have to buy all these different chemicals in order to create our different slides. And then for our mechanical system, it's around $3,600, with most of the money coming from our spectrometer, which costs about $1,500, and the rest has to do with like fiber optic cables and like 3D printing special filament for our slide holders and things. And I'd like to pass it to Will to wrap things up.
So our bigger picture is that our device eliminates the need for heavier bulker devices for heat management and satellites. With our device, our potential device, we can eliminate the needs for heat sinks, heat pipes, or basic mechanical heat removers from our space satellites. And in real life, we have these things happening right now. We have smart windows replacing blinds. We have variable electrical and chromic devices replacing your shutters for your airplane windows. And we have train windows starting to do the same thing. It turns out that this mechanical device will have a lower material cost than a typical blind, overall material cost. It'll have a higher reliability over its entire life cycle, and its functionality and optimization will be on top because it is programmed. You can program it with an electrical circuit or with controls, and you can optimize it to whatever function you need. So in our case, we can let in light if we want to in our spacecraft. We can let in heat, as much heat as we want into in our spacecraft, and we can reject as much heat as we want to in our spacecraft. With that said, thank you very much. Do you have any questions?